In our last episode, we tried to wrap our heads around a number so large it almost stops meaning anything. 2 trillion galaxies. Not counted one by one, but carefully estimated, scaled, corrected, debated, and still probably an underestimate. But what happens when the deeper we look, the stranger those galaxies become? Because today, we're not just talking about how many galaxies exist, we're talking about one that shouldn't exist the way it does. Take a moment and picture this. You're looking at an image of a galaxy that formed nearly 13 billion years ago, when the universe was still in its cosmic infancy. It had barely learned how to switch the lights on. And yet, this galaxy doesn't look like a newborn. It looks grown up. It's massive, structured, mature, far more evolved than anything that young has any right to be. And here's the uncomfortable part. This isn't a one-off cosmic fluke. Ever since the Webb telescope unfolded its golden mirrors and began peering deeper into space than any telescope before it, it has been quietly, and sometimes not so quietly, rewriting the story of the early universe. Webb hasn't just pushed boundaries, it's stepped over them. And now the situation has escalated. A Nobel Prize-winning physicist has publicly stated that Webb's observations may be forcing us to rethink some of the most fundamental assumptions about how the universe works. Not just galaxy formation, not just early cosmic structure, but the very nature of the universe itself. For over a century, astronomers have operated under a comforting assumption that on the largest scales, the universe is uniform. No matter which direction you look, things should average out. The same density of matter, the same temperature, the same expansion rate. This idea is known as isotropy. It's elegant, it's simple, it's neat. Gravity works the same everywhere, so the cosmos should look balanced and orderly when viewed across enormous distances. And for decades, the cosmic microwave background, the faint afterglow of the Big Bang, seemed to confirm that. The universe looked remarkably smooth and consistent in all directions. Case closed, right? Well, not anymore. New research recently published in the astrophysical journal Letters suggests something deeply unsettling. The universe may not be expanding at the same rate everywhere. Let that sink in. The speed at which space itself stretches could depend on which direction you look. If that's true, then the universe isn't perfectly uniform after all. And that's not a minor adjustment, that's foundational. As Nobel Laureate David Gross described it, this isn't just a small inconsistency to tidy up later. It could represent a full-blown cosmological crisis. To understand why that word isn't exaggerated, we need to rewind a century. Back to the 1920s, back to Edwin Hubble. Using the most powerful telescope of his time, Hubble discovered that distant galaxies were moving away from us, and the farther away they were, the faster they receded. It was the first clear evidence that the universe is expanding, not exploding outward from one point in space, but expanding everywhere, in all directions, uniformly. That discovery became the backbone of modern cosmology. It shaped the Big Bang theory. It defined how we measure the age of the universe. It anchored everything. And now, Webb may be telling us that expansion isn't perfectly uniform after all. If that turns out to be true, then the neat, orderly picture we've relied on for generations might need serious revision. And that's what makes this discovery so powerful. We started this series by counting galaxies. Now we're questioning the rules that govern them. And the deeper we look, the more the universe seems willing to surprise us. From the discovery of cosmic expansion, scientists realized something extraordinary. The universe has not existed forever. If space is stretching today, then rewind the clock far enough, and everything must once have been much closer together. That simple idea gave us a finite cosmic age. At the heart of this calculation sits a crucial number, the Hubble constant. Think of it as the universe's speedometer, or better yet, its cosmic clock. By measuring how fast galaxies are moving away from us, astronomers can effectively run the movie backward and estimate when it all began. But here's the problem. For decades, that clock hasn't agreed with itself. Early measurements from the Hubble Space Telescope revealed an uncomfortable range. Depending on how you measured it, the universe could be as young as 9.7 billion years, or as old as 19.5 billion years. That's not a small rounding error. That's a multi-billion-year identity crisis. In fact, at one point, some stars appeared to be older than the youngest estimate of the universe itself, which is awkward. So astronomers refined their methods, narrowing things down using two gold standard approaches. The first method looks at tiny temperature ripples in the cosmic microwave background, the faint afterglow of the Big Bang, mapped in exquisite detail by the European Space Agency's Planck satellite. That approach gives a Hubble constant of about 67 kilometers per second per megaparsec. The second method focuses much closer to home. It uses Cepheid variable stars and certain types of exploding stars, supernovae, as standard candles. Because we understand how bright they truly are, we can measure their distance by how bright they appear. That method consistently gives a higher value, about 74 kilometers per second per megaparsec. 7 kilometers per second per megaparsec might not sound dramatic. In cosmology, it's huge. At first, many scientists assumed it must be measurement error. Instruments can improve. Data can be recalibrated. Maybe one method just needed refinement. But over time, the gap didn't shrink. It solidified. As astrophysicist Adam Rees has pointed out, we've now explored the full range of possible observational uncertainties. The discrepancy isn't going away. And then came the Webb telescope. With sharper resolution and unprecedented sensitivity, Webb has helped confirm that this tension is real. The universe does not appear to expand at a single, perfectly consistent rate everywhere we look. If that's true, the consequences are profound. For over a century, cosmology has relied on what's known as the cosmological principle, the idea that, on large scales, the universe is homogeneous and isotropic. In simple terms, roughly the same everywhere and roughly the same in every direction. But what if it isn't? If expansion varies depending on location, then our assumptions about the universe's age, its size, and even its long-term fate may need serious revision. And that leads to an almost unsettling question. Why would the universe expand differently in different regions? One possibility involves dark energy, the mysterious force thought to be driving cosmic acceleration. Maybe dark energy isn't perfectly uniform. Maybe it fluctuates subtly across space, stronger here, weaker there, gently reshaping the cosmic landscape in ways we've never considered. If so, the implications are staggering. If the universe isn't uniform at the largest scales, then perhaps the laws of physics we measure locally are just that, local. Beyond our observable horizon, gravity could behave differently. Fundamental constants might vary. The structure of reality itself could be more flexible than we've assumed. It sounds almost surreal. But this is the debate Webb has reignited. For generations, the idea of a smooth, balanced cosmos guided every cosmological model we built. Now that foundation is being questioned, and once again, we find ourselves in a familiar position in science, standing at the edge of certainty, staring into something larger and stranger than we expected. As we look at the distant galaxies Webb has revealed, we're reminded of something humbling. We are tiny observers inside an evolving universe, conscious fragments of stardust trying to decode a story written across billions of years. Every discovery brings clarity, and at the same time, deeper mystery. The universe is not just expanding. Our understanding of it is too.